As you can remember, on our previous lecture, we have learned electric flux. Electric flux, this can be written as Fe, and this is equal to surface integral E ds. Okay, and let's try to calculate electric flux of one point charge through closed spherical surface. I'll try to draw a picture. I'll try to draw a picture to show what I mean. Show what I mean by this. I mean something like this. Closed surface S. Closed surface S. It has radius. It has radius R. It has radius R, and we have a point charge QS. Point charge QS in the center of this closed surface. In the center of this closed surface. And from our previous lecture, you know that electrostatic field intensity in this case is equal to 1 divided by 4p epsilon 0 multiplied by q s. Sorry, I mean absolute value, not vector. Divided by r to the power of 2. It is absolute value of electric field intensity on this surface, because a point of surface has this distance from center is r. Distance between surface S and its center is r. And how to calculate electric flux in this case? In this case, it will be something like it will be integral, but I will draw this round. This round means that we have closed surface. And how to calculate this? Here we have simple case. Because I'll draw this vector of electric field intensity. Vector of electric field intensity in each point of surface is perpendicular to this surface. Vector of electric field intensity is perpendicular to the surface S. And it means that element of this surface, element of surface S, it may be signed may be signed as ds, some ds element of surface. It is also perpendicular to the surface, and it may be signed as ds. And from picture we can see that vectors E and vector ds, vector E and vector ds have the same direction. These vectors have the same direction. Same direction maybe signed as these two arrows directed from down to up. And from here we can make a conclusion that a dot product, E ds, dot product E ds is equal to E ds, cosine 0, because if two vectors have the same direction, the angle between them is equal to 0. So this is equal to E ds. This is equal to E ds. And we can use this result. Here to simplify our surface integral. So it will be E ds. It looks almost the same, but here we don't have any vectors. So the integral was significantly simplified. It was significantly simplified because it is much more simpler to work with scalars than with vectors. And moreover, absolute value of vector E, as we can see from this formula, is the same for each point of surface S. So it doesn't depend on element ds. It doesn't depend on this. So it means that E may be written outside of the integral. It may be written outside of the integral. So it will be E multiplied by integral S ds. S and ds. And this integral is just the same as it is just the same as sum of all elements ds. So it will be just area of surface S. So it is equal to E multiplied by S. Is equal to E multiplied by S. And as we know, area of sphere is equal to 4p radius r to the power of 2. So it will be 4p r to the power of 2. This area of spherical surface, area of the sphere, and multiplied by E. And of course we can substitute this here. We can substitute this, and we will get 4p r to the power of 2, 4p r to the power of 2, and multiplied by this value. And after simplifying, we'll have that electric flux is equal to Qs divided by epsilon 0. So result doesn't depend on radius of this spherical surface. And what do we have? We have got a result that is a partial case of more general result that is known as Gauss flux law or Gauss flux theorem. Gauss flux law for electrostatic field intensity. Gauss flux law. Gauss flux law. I mean integral form of Gauss flux law for electrostatic field intensity. For electrostatic field intensity. Integral form of Gauss flux law for electrostatic field intensity. We have not enough time to prove this in general case. We have just considered only partial case of this. But in general case, this law will be true for any closed surface and for any charge inside this closed surface. And lower index S near the charge Q means that we take into account only charges inside closed surface. And the electric flux of charges that are outside of closed surface is equal to 0. So here we have only charges inside a closed surface. So and if we have some volume distribution of electric charges, we may write this via triple integral. Here we have Vs. Vs is volume inside the closed surface. Rho Q is charge density. Rho Q is charge density, and differential dV. Differential dV. And differential dV. differential dV. Okay, do you have any questions?
Nope, for me.
Okay, thank you. And of course, if you have integral form, of course, we should have a differential form. Of course, we should have differential form. Of course, we also have differential form. Differential form. And how to get differential form? Maybe you can remember from your calculus course. Maybe you can remember Ostrogradsky-Gauss theorem. Ostrogradsky-Gauss theorem. According to this, surface integral along the closed surface, surface integral of E ds is equal to triple integral. This is equal to triple integral Vs, and here we will have a divergence. Here we will have divergence of E. This is Ostrogradsky-Gauss theorem. Ostrogradsky-Gauss theorem. And if we substitute this here, we will get that this triple integral is equal to 1 divided by epsilon 0, 1 divided by epsilon 0 multiplied by triple integral Vs rho q dV, rho q and dV. And from here we will get differential form of Gauss flux law for electrostatic field intensity. So we will have divergence E. Divergence E is equal to rho q divided by epsilon 0. Q divided by epsilon 0. This is a differential form of Gauss flux law. Sometimes this Gauss flux law is useful for calculating of electrostatic field of some systems of electric charges, especially if distribution of electric charges have some symmetry. For example, plane symmetry or axial symmetry. In all these cases, Gauss flux law is useful. And if we have defined electrostatic field, differential form of Gauss flux law allows us to define charge density. That produces this electrostatic field. That produces this electrostatic field. Yeah, I will clean the screen. I'll clean the screen and what else can we do? We can remember that the divergence E. We can remember this from calculus. That divergence E is equal to Hamilton operator or del operator multiplied by E. And we can also remember from our previous lecture that E, electrostatic field intensity, is equal to minus gradient of electrostatic potential. And after substitution, we will get that minus del operator and another del operator and phi. Okay, and let's write this in extended form. It will be minus d dx e plus d dy j and plus d and dz k. And another del operator will be the same. It will be the same bracket again. And phi. Okay, and if we remember some properties of EJK, of these orts of coordinate axis, we will have that scalar product I and I is equal to J and J, and this is equal to K and K, and this is equal to 1. This is equal to 1. And if we have product E J or E K or J K, this will be equal to 0. And if we take into account this, we will get that it will be minus d2 by dx2 plus d2 by dy2 and plus d2 by dz2 phi multiplied by phi. And this is inside these brackets. We have obtained Laplace operator. So it is just minus Laplace operator of electrostatic potential. So we have got that divergence E. That divergence E is equal to minus Laplace phi. And after substitution of this here, we have got Poisson's equation. We have got Poisson's equation. Poisson's equation. And according to this equation, Laplace phi is equal to minus rho q divided by epsilon 0. It allows to find distribution of electric charges if we have defined electrostatic potential. We can use Poisson's equation to find the distribution of electric charges. Okay, do you have any questions?
So far, so good.
Okay. Okay. If it is good, it is necessary to clean some place. And continue. Before this moment, we have learned only electrostatic field in vacuum. So we didn't take into account any substance, media, but of course, we also may have electrostatic field in different materials, in different media. And maybe you can remember that there are three types of materials, three main types. They are conductors, semiconductors, and dielectrics. Conductors, semiconductors, and dielectrics. Conductors can easily conduct electric current, and dielectrics are bad conductors. We have a little possibility to conduct electric current through dielectric. And semiconductors are between conductors and dielectrics. And why conductors can conduct electric current? Because there are free charges inside them. What are free charges? Free charges are charges that may easily change its place. And if we know, as we know, electric current is a flow of electric charges in some space. Electric current is flow of electric charges, is a directed flow of electric charges. And of course, to obtain a flow of electric charges, it is necessary to have free charges. And conductors have many free charges, and dielectrics have only little number of free charges. But it doesn't mean absence of charges. It doesn't mean absence of charges because all substances are consisted of atoms, and each atom consists of positive nuclear and negative electrons around this nuclear. And of course, we may have we may also have iron crystals. For example, sodium chloride or simple salt. It consists of positive sodium ions and negative chlorine ions. This is a crystal of salt or sodium chloride. And of course, substance may contain polar molecular. For example, molecular of water. Molecular of water, it consists of negative oxygen and two positive hydrogens. So as dielectric in general, dielectric is electrically neutral, but it consists of pairs. It consists of pairs of negative and positive charges. But these charges cannot be easily moved. And because of this fact, they are called bound charges. Bound charges cannot be easily moved in space. So it is not easy to push them to change its place in space, or to change their position. And because of dielectric is electrically neutral, and we may represent the bound charges as some number of pairs of positive and negative charges. It will be useful. It will be useful to consider. Electric dipole. What is this? Electric dipole. Electric dipole. Electric dipole is just a pair of positive and negative charges. So here we have positive charge plus Q, negative charge minus Q. negative charge minus q. And we have vector that begins on negative charge and ends on positive charge. And we will sign this vector as L. And the absolute value of vector L is infinitely small. Or for real situation, it is just small. Just small enough in compare with some other distances in system. So electric dipole may be characterized by some dipole moment. But let's write lower index I here. Lower index I and dipole moment. Dipole moment is P I, and this is equal to Q I multiplied by L I. Of course, the dipole moment has the same direction as vector L I. So it is directed from negative charge to positive charge and is equal to this product. So this is electric dipole. This is electric dipole moment. Maybe dipole will be with double L. Electric dipole, no, dipole moment. Yes, pole with index E because with lower index E dipole. This will be correct. Electric dipole. Electric dipole. Okay, and do you have any questions about this? So bound charges inside dielectric may be represented as some amount of electric dipoles inside this. And let's try to imagine what will happen if we put electric dipole into internal electrostatic field. Let's try to imagine what will happen in this case. I'll draw a new picture. With electric dipole plus Qi minus Q minus Qi plus Qi and minus Qi. And here, of course, we have Li. And let's turn on external electrostatic field. 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 And in this case, of course, this field will push positive charges to the right. It will push positive charges to the right and negative charge to the left, according to the direction of a field and signs of charges. So here we have some electrostatic force F, and here we have minus F. Here we have minus F. And as we can see, electrostatic field tries to orient dipoles, in the direction of the field. So if we put dielectric into electrostatic field, we will get redistribution of bound charges, inside dielectric. Because of course bound charges cannot change their position, but they may be moved a little. In relation to their initial positions. They will be moved a little, so they will be redistributed, and as a result of this redistribution, we will get the situation when the most of dipoles will be oriented as electrostatic field. Most of dipoles will have the same orientation as electrostatic field, or the same direction, and it means that some polarization occurs, because the described redistribution of electric charges, of bound charges, is known as polarization, and this polarization may be described by polarization density. Polarization density. Polarization density. Polarization density. It is vector P. Polarization density is equal to sum of dipole moments. Inside volume delta V divided by this volume delta V. Sum of dipole moments inside volume delta V divided by this volume. Okay, do you have any questions about this? No questions. Okay, if there are no questions, it is necessary to few words about the connection between electrostatic field and the polarization density, because calculation of this direct calculation of these dipole moments of bound charges, direct calculations, it is difficult, or sometimes it is even impossible. But we know from experiment We know from experiments that in some simple cases, we have simple connection between polarization density and electrostatic field intensity. In simple cases that are called isotropic dielectrics. I will write this for isotropic dielectrics. For isotropic dielectrics, we have a simple connection. Simple connection. So P is equal to kappa epsilon zero multiplied by vector E. Kappa epsilon zero multiplied by vector V. So epsilon zero is electric constant. We have already learned this, and kappa is electric susceptibility. Kappa is electric susceptibility. Kappa is electric susceptibility. Kappa is electric susceptibility. For isotropic dielectrics. And more difficult cases we will not learn because we don't have enough time, and we don't need to know such difficult things. Okay, and let's try to consider redistribution of electric charges via polarization more particularly. Let's define some surface. Let's define some surface in the electric. Let's define some surface S in the electric. Let's define some surface, and let's turn on. Let's turn on electrostatic field E inside this dielectric. Because of these negative charges will move to the left a little bit. Negative charges will move a little bit to the left. So minus Q I and some L2. And positive charges will be moved to the right on distance L1. It is QI. Okay, and the question is how to define a change of bound charges. Change of bound charge on one side of of the surface. How to define change of bound charge? This change, of course, will be equal to change of bound charge will be equal to minus charge that passed through surface S. This surface S. So it is necessary to calculate. These charges that passed through the surface. And how to do this? It may be done. With concentration of electric charges. What do I mean? It will be minus concentration of electric charges multiplied by delta V. Where delta V is minus delta V is delta V1 plus delta V2 and what is delta V1 and delta V2? These values, this value delta V1 and delta V2 is I'll try to no, it is not what I want. So this is this rectangular is delta V2. This delta V2 and this is delta V1 and their sum is delta V. And as you can see from the picture, it will be minus n area of surface S multiplied by L1 plus L2. L1 plus L2. And if we sign their sum L1 plus L2 as Li, we'll get this. And now it is necessary to remember what concentration of electric charges is. This is sum of electric charges inside volume delta V divided by this volume delta V. So from here we will have that this is sum of electric charges as LE. And if LE is the same for all electric charges, and we may consider that it is the same because if we define Li as some average displacement of bound charges, if Li is the average value, we will rewrite this. We will write this as Qi Li divided by delta V multiplied by S. And but we know that that product of Qi and Li is electric dipole moment. So it will be minus some I P I divided by delta V S. And now we can remember that sum of dipole moments divided by volume delta V that contains these dipole moments is equal to polarization density. So it will be minus PS. And of course, according to this equation, the direction of polarization density and the direction of polarization density is the same as direction of electrostatic field intensity. So polarization density is directed from left to the right in the same direction as electrostatic field intensity. And we may define of orientation of surface S by vector ds. Its absolute value is equal to area of element ds, and its direction is normal to surface S. So according to this picture, vector P has the same direction as vector S. And of course, it means that scalar product of P and S will be here we have plane surface. That it means that I can write this just as without differential. So absolute value of vector S is the same as area of the surface, and its orientation is this vector is directed normally to the surface, and its direction is the same as direction of vector P. And because of this, we have that P as cosine 0, and it will be P S. It will be P and S. So from here, we can use this we can use this equation to write this in vector form, minus ps. Okay, do you have any questions? So we have got change of bound charges in the left part of dielectric, left in relation to the surface S. So change of bound charges is equal to minus ps. And of course, if we consider some more general case, if we consider not a homogeneous field and not plane surface, it is necessary to consider infinitely small part of this surface. It's necessary to consider an infinitely small part of this surface. And for infinitely small part, we will have the same relation. So change of bound charge is equal to minus p and ds. Minus p and ds. And this will work for non-homogeneous field and for any surface. For any surface S, not just for plane surface. Not just for plane surface. So from here, after integration, we will have that polarization flux Fp is equal to surface integral along closed surface S P ds, P and ds, and this will be minus q, minus bound charge inside, closed surface S, and it will be equal if we have some bound charge distributed in some way in volume. We can rewrite this via triple integral. Triple integral Vs rho q. This sign above rho or above q means that we have bound charge. So this sign above the charge means that we have bound charge dv. So we have obtained integral form. This is integral form. Of Gauss flux law. Integral form of Gauss flux law for polarization density. 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 Integral form. integral form, and of course, if there is integral form, there also should be differential form. Differential form may be obtained from integral form by using Gauss-Ostrogradsky theorem. And if we use this, we will get that divergence P is equal to minus rho Q. Minus rho Q. Minus rho Q. Minus rho Q. Now, differential form. Differential form of Gauss flux law for polarization density. Polarization density. Okay, do you have any questions? No questions. No questions. Okay, and let's use this. Let's use this relation again. Let's consider some surface of the electric in vacuum. Let's consider some the electric in vacuum, and inside the electric we will have some polarization density. We will have some polarization density P. Some polarization density in vacuum. Some polarization density, and according to this, we will have change of some change of bound charge, change of bound charge in volume of the electric, and according to the law of conservation of charge, this bound charge will appear on the surface of the electric. If it reduced in volume, it will appear on surface. So we can write that some surface. How to define this? Maybe Q with lower index sigma. Some surface charge will be equal change of charge on surface, the Q sigma. It is equal to minus the Q in volume, and it will be P multiplied by ds. Where ds is element of this surface. It is element of this surface ds. And this is always normal to the surface. And this may be written in a scalar form. if we consider Pn, Pn is a projection of vector P on normal direction to the surface. So this is projection of vector P to the normal direction. And from this we will get that this projection is equal to P is equal to d q sigma ds, and this value charge, bound charge on the surface divided by area, it is surface density of bound charge. Surface density of bound charge. Surface density of bound charge. It will be some sigma. It will be some sigma q. Lower index q means that we have surface density of charges. Because of this, we use lower index q. Okay, and what will happen if we have general case? If we have general case, not only the electric vacuum, not only surface between the electric and vacuum, and if we have general case of surface between two dielectrics, we'll have two polarization densities. First will be P1, and the second will be P2, and the second will be P2. And according to this formula, polarization density will be sigma q is equal to P1n minus P2n. And where to use plus, where to use minus, it is explained by the picture. So this is a surface density of bound charges. Surface density of bound charges. Surface density of bound charge. Okay, do you have any questions? Do you have any questions? No questions. Okay, if there are no questions, let's frame this in red. And now I can clean some. Place on the screen. And what do we have? Now we have several formula. We have a few formula, and let's consider general case. If we have free and bound charges. if we have both free and bound charges. And let's use integral form of Gauss flux law for electrostatic field intensity. But now we take into account. Now we will take into account bound charges. Bound charges. So in this case, we will have that electric flux. This is the surface integral E ds, E and ds, and this is equal to. We have to take into account free charges and bound charges inside closed surface S, and divided by epsilon 0. And as you know, for bound charges, we can use this Gauss flux law for polarization density. Gauss flux law for polarization density may be used for bound charges. So it will be Qs minus surface integral along closed surface S P ds and ds divided by epsilon 0. Divided by epsilon 0. Divided by epsilon 0. And from this equation, we will get, it may be written in some another way, as surface integral epsilon 0 E plus P ds and equal to free charge inside closed surface S. Okay, do you have any questions about this? Okay, and now it will be useful. It will be useful to introduce new value that is known as electric displacement vector. Electric displacement vector and or what is the same, electric induction vector. Electric induction vector or electric induction vector. This is value inside these brackets. This is electric displacement vector, and it may be written as D. Vector D is equal to epsilon 0 E plus P plus P plus P plus P plus P. And if we use this value, we will get integral form you get integral form of Gauss flux law for electric displacement vector. For electric displacement vector. Displacement vector. Gauss flux law for electric displacement vector. So it will be F d is equal to surface integral S d ds, and this will be free charge inside closed surface S, and this will be equal to triple integral rho q d v. So this is integral form of Gauss flux law for electric displacement vector. And the differential form may be obtained from integral by using Gauss-Ostrogradski theorem. Differential form of Gauss flux law for electric displacement vector. This will be divergence. Divergence d. Divergence d is equal to rho q. Is equal to rho q. Is equal to rho q. Okay. Do you have any questions about this? Do you have any questions? Nobody hears me. Nobody hears me. It's a pity. Okay. And what is the connection between electric displacement vector and electrostatic field intensity? We can remember that polarization density may be written for isotropic dielectrics as kappa epsilon 0 e. Kappa epsilon 0 e. Let's substitute this here. We will get that d is equal to epsilon 0 e plus p, and it will be the same as epsilon 0 e plus kappa epsilon 0 e, and it will be 1 plus kappa 1 plus kappa epsilon 0 E. And it can also be written as epsilon 0 E. Epsilon 0 E. Epsilon 0 E. Where epsilon is relative permittivity. So we have connection. We have connection for isotropic dielectrics. For isotropic dielectrics. For isotropic dielectrics, d electric displacement vector is equal to this. Where epsilon is equal to 1 plus kappa, and this is relative permittivity. Relative permittivity. And of course, in vacuum, there are no any bound charges. So in vacuum, polarization density of course equal to 0, and it means that in vacuum electric susceptibility will be equal to 0, and it means that in vacuum relative permittivity will be equal to 1. If kappa is equal to 0, epsilon will be equal to 1. So we can also write that in vacuum, in vacuum, kappa is equal to 0 and epsilon is equal to 1. Epsilon is equal to 1. Is equal to 1. Okay, this is enough for today. And do you have any questions? Do you have any questions? Okay, if there are no questions, I hope to meet you tomorrow when we will do some exercises. And thank you for your attention.